So welcome back. Let's start today's class with some of the feedback chits. So a few of you said that this EPR matrix EPR matrix that I wrote down and this argument that I made about the rank, there were a couple of you who felt that that was not clear. So let me just tell you what the argument is. It's actually really simple. Okay, so maybe I'll just use the title slide here and then we can erase that. So if you remember what the EPR pair was, right? So it's 1 over root 2 0 0 plus 1 1, isn't it right? So all that I had been saying was that think of this EPR pair in terms of the basis vectors that we had developed. So you remember that for n dimensions we said the basis will be in 2 to the n dimensional space, right? So in particular for dimension 2, what was the basis? So it was 1 0 0 0, right, 0 1 0 0, 0 0 0 1, okay. Yes, very good. This was the basis, right? So now if I express the EPR pair along this basis, what are the coefficients? Just 1 here and 1 here, right? And then 0, so for uniformity I'll write it in the same place. So these are the coefficients. So that's how I got this matrix 1 0 0 1. This was the question that was being asked in some of the feedback chits, and it's obvious that the rank of this EPR matrix is 2. Whereas what I had also claimed was that if I take the tensor product of two vectors, the rank of that is only going to be 1 at most. Okay, therefore we arrive at a contradiction. Is it now clear? Is it clear or not clear? So what we said was that if I have two two quantum states, right, whatever they may be. So remember then we wrote alpha 1, beta 1, whatever, alpha 1, alpha 2, right, beta 1, no, alpha 1, beta 2, right, and then alpha 2, yeah. So any tensor product, when I write it out, right, now I can write this again as a matrix, just as I took this vector and wrote this as a matrix, right, I can similarly take this vector and write it as a matrix, right. So that's just a question of rearranging the entries, isn't it? And now my claim is that the rank of this matrix, no matter what the alphas and betas are, the claim is that the rank of this matrix cannot be more than 1, and this is because the rank of a tensor product, right, is going to be the rank of the two component vectors. So the vector by definition can only have rank 1, right. So that's all there is to it. So do you see now the contradiction? Yeah, okay, much better. So this was all I was saying, that basically with EPR we can see that you get rank 2, whereas for any tensor product you cannot get rank 2, therefore EPR cannot be a tensor of two vectors. Okay, so now let's erase this. Okay, so this was a couple of the questions. One question was how are phase shifts useful? So we'll talk about that in today's class. In any event, sort of before thinking about why phase shifts are useful, a general thing is just that phase shifts occur, right? So we want to model them. But anyway, we will see why they are useful. Okay, very good. So today's topic is going to be very exciting. It's about finally how do I get beyond classical, right? I'm itching to get beyond classical computing, so let's do it. So first we will, we have to pick up where we left off. So if you remember, what we were talking about was Toffoli gates, right, and how they can simulate the AND gate, the NAND gate, as well as fan out. This is what we said, right? And good. So you know, this is the definition of fan in, fan out, and this is what I said you can do in order to get fan out. And the question that I left you with is, why is this not a contradiction to the no cloning theorem? So who's going to answer that? What he said is that fine. So this is true for this picture that we have. This holds for classical bits. Yes, you know, if A is 0, then I get 0 0. If A is 1, I get 1 1. But now to contradict the no cloning theorem, I should be able to use this for any arbitrary state. And if I take some arbitrary state alpha 0 plus beta 1, then what is going to happen is I am going to get basically alpha 0 0. So if I just think of 0, right, that, so basically A equal to 0, if A equal to 0, right, then my A and 0 over here is going to give me what? Then I get 0 0, right, and if A is equal to 1, then I get 1 1, right. So in general, if I take any alpha 0 plus beta 1, then by linearity I get alpha 0 0 plus beta 1 1, and this in particular is not equal to alpha 0, sorry for the for running out of space here. So okay, so if I have alpha 0 plus beta 1, right, then I get alpha 0 0 plus beta 1 1. And this in particular is not equal to alpha 0 plus beta 1 tensor alpha 0 plus beta 1. Do you see that? So therefore you did not clone anything. Any questions about this? It's clear? Okay. Okay. So yeah, so there is no contradiction. I don't know if this is a happy face or a sad face, but there is no contradiction. Okay, so now let's have some fun with circuits. So here's the circuit. So who can tell me what this circuit computes? I mean, what should the output state be? What is phi? Maybe it's always good to go step by step. So what is phi and what is psi? So what is phi going to be? So it's going to be the Hadamard of 0 tensor 0, right. So this is H 0 tensor 0, and this is nothing but plus 0, right, which is nothing but right. And now this psi, what do I get? So you know, basically I have the C naught gate over here, and I am going to have the first bit be the control bit, right. So it's the C naught of this, right. So what is that going to be? So since the control bit is 0 over here, this is going to stay 0, and since the control bit is 1 over here, this will flip the output here. Okay, so I will get the EPR state. Any questions? Okay, so then another interesting thing here was that this EPR state has some really nice properties. So in particular, here's an exercise. I want to apply the Hadamard transform to each bit of the EPR. Can you tell me what I'll get? So I'll write this here. So I'd like everyone to work this out. Okay, so we pass this through H tensor H, that is apply H to each qubit. So I'll work it out over here, but I'd like you to work it out yourselves and then compare, right? So what do I get? So H tensor H of okay, so what is this going to be? So H tensor H of 0 0 will give me plus plus, right, and H tensor H of 1 1 will give me minus minus. Okay, so this is going to be 1 over root 2, 1 over root 2 0 plus 1 over root 2 1 . Okay, so as you see here, hopefully you also got the same thing. So basically if you perform this operation, then you just recover the original EPR bit, and this is surprising, right? But so the point of this exercise is just that counterintuitive things happen. So you're not, at least to me it does not seem intuitive that I should pass a 2 qubit state through the Hadamard transform and get back the same state, right? But yeah, with EPR this is happening. All right, good. Any questions about what we have seen so far? So now we are finally ready to discuss how classical computation will be captured. Okay, so let's be formal. So what is it that we want here? We want that given a classical function, let's say for simplicity a Boolean function, so f01 to the n to 01, we want to evaluate this now using a quantum system, right? And what this means in our language is that therefore there should be some unitary u such that when I apply u to x, I get the state fx, correct? And the fact that I need a unitary for this operation means that this function needs to be bijective, right? And if a function is bijective, what does it mean? Basically, I can reverse the computation as well, right? So this brings us to the notion of reversible computation, which we will talk about briefly next. So it turns out that reversible computation has actually been studied even without the context of quantum computing for a long time, and the reason for this was that if I lose information in a computation, again from the physical point of view, if we lose information, right? So for instance, if we take a 2-bit input and we give a 1-bit output, like the AND gate for instance, right, then a certain amount of energy must be expended whenever you lose information. So the idea of reversible computation was that, can we prevent this energy from being lost? So can we construct our computation in a reversible way? So it has been studied in this context already for a long time, and in the context of quantum computation, obviously we need reversibility, right, because we have to work with unitaries. So let's define reversible computation first. It's exactly what you would expect. What would you expect? Well, just that it should be reversible, which means that the number of inputs and the number of outputs should be the same, and there should be a bijection between the inputs and the outputs, and that's exactly what this definition is saying. Okay, so now having defined a reversible gate, it is something that can be implemented by a unitary transformation. And how do I implement the reverse now? Well, if I perform a computation, how do I perform the inverse of the computation? Just by inverting the matrix and applying it again. So it's very, very natural and structured, right? And we have already seen examples of this. So now we are just giving it a name. So for instance, we properly studied this Toffoli gate, and this we already saw that it is an implementation of AND gate, NAND gate, whatever you want to call it, right? NAND is more suitable for us right now. So it is already a reversible implementation of the NAND gate, right? You can see from the truth table that the properties that we require, of it being bijective and number of inputs outputs being the same, this holds, right? So good. So this is just about this is a reversible computation of the NAND gate. Now in general, I could generalize this to reversible computation of any circuit, I claim. Okay, so there are couple of things that we want to talk about here. So one is that the NAND gate in classical computing is a universal gate. So why is that? So basically I want to claim here that NAND gates are universal for classical computing. And what does this mean? It means that if you give me any circuit which has AND gates, OR gates and NOT gates, I could replace this all these gates by NAND gates. Of course, I can't just throw out the AND OR gates and put in NAND gates, that would make no sense, but I could have like a little gadget, right? So for every gate that I have in my underlying circuit, I can have a little gadget circuit which implements that gate using NANDs. And because we have an audience which is largely not of CS folks here, I'll just show you the broad idea why this holds. Okay, so it's very simple. So first I want to eliminate OR gates. Okay, so I'm just going to start with one gate at a time, and I'll show you how to remove it using the NAND gate. So in order to eliminate the OR gate, it turns out that we can use this De Morgan's law. So if you haven't seen this before, I encourage you to look on Wikipedia. But what this lets me do is that it lets me express OR x1 x2 as not of and of not x1 not x2. Okay, so a simple way to verify this is just to write down the truth table and see. I will not do it in class. Okay, so we can eliminate OR like this. Now the next thing to eliminate is AND. So eliminating AND is extremely simple. What should I do? I want to eliminate AND by using NAND. What should I do? Exactly, right? So just not of NAND. So that was easy. And now finally I want to eliminate NOT. So there are multiple different ways to do this. One way to do this is to just hardwire one of the NAND gate inputs as 1. So now what happens is that if I give input X, then what I get as output is not X. Okay, so what this shows is that if I can simulate NAND gates, right, then I can simulate any classical circuit. So moreover, we have that NAND gates, we saw a nice reversible way to simulate them, right. So we can use the unitary transformation in order to capture that. In fact, we saw that unitary in one of the previous classes. So now here's another small example. So these are 3 NAND gates. Can you draw the reversible implementation? So again I'll do it here, but I'd like to do it yourselves. Okay, so all these 3 are NAND gates. So what am I hoping to do here? I would like to use the Toffoli gate in order to sort of simulate this circuit, and it's very easy, right. So let me give some names to these wires, A, B, P, Q, let's say. Okay, so now what does my quantum circuit look like? So this is my Toffoli gate. So if you remember, the Toffoli gate is going to just replicate the first 2 inputs, and in the last wire it will give you the NAND, right. So let me do this twice to get both my NAND gates from the original circuit. So now I have PQ and I have my third bit as 1. So once again these go all the way out, and now here I get NAND of PQ, right. And now I would like to have another Toffoli gate here. So now what are my outputs? It's NAND AB, NAND PQ, and NAND of, so let me call this delta 1 and I'll call this delta 2, and my output is NAND of delta 1 delta 2. Okay, so this is how I got a reversible implementation of a given circuit. Okay, and I wanted to do this concretely because it's good for us to see what this looks like. Okay, and in general we can prove a theorem which says that if I have a given circuit, then the reversible analog will not be too much bigger. So up to just a constant factor. So I will not prove this here in class, but there is such a thing.